Okay. Um, so the thing that I was trying out a little earlier, it's the table for the merge, the list merge sort. Um, if you remember, list merge sort was a variation of the natural two-way sort and merge sort and the straight two-way merge sort where you've got links that are updated instead of having this extra storage space. And there's a table, I think it's table 3 in that section. And I think Miguel commented about juggling the different number of things you have to remember or keep track of at once. I think that it was that table that you were talking about. And I tried to expand the rows of that table to show what's happening in each intermediate step. And it turns out to be, at least I found, it's much more sneaky than I thought it was. Even after I had implemented the algorithm in C and I had posted that on the Meetup page. So that's been there for a while, but when I started to actually see what's happening, it was pretty interesting. So I think I'm done with it. I'll show it to you. If somebody else joins, then we can just wait a couple of minutes, get some feedback on it, and then I'll post this table, the expanded table to the GitHub repo, and you can see it yourself.
Yeah, that's great, because that's one of the things that I dreamed about doing. Like expand the table to just not having because I mean, it's kind of easy to follow the little table they had, but not easy to follow the rest of the stuff with the table, right? You can say, yeah, I can see how you get there, but I mean, I can see that you should get there, but how the hell did you do that? I don't know what was subtracted and what was added. It's tough. So it's great.
Yeah, so that's exactly what I discovered. And again, I thought I understood what's happening, but when I saw what's actually happening, when I expanded the rows, there were a couple of surprises for me. The way the lists are behaving and they're getting updated, and so it's interesting.
This is figure 33, was it? The one with the sort of columns of linked lists.
Oh yeah, that's right. I think it is. No. That's the radix. That's the radix sort.
All right, you're talking about list merge.
I'm talking about the list merge sort that is.
That was one with all those small integers. So many integers everywhere. Table 3 on page 165.
Exactly. Table 3 on page 165. Yeah. And it's exactly what Miguel says, that, when you look at this table, you kind of understand what's happening in each pass, and, you can sort of see the rationale for these numbers. But it's really the intermediate steps within each pass that are really interesting. So that's what I tried to do. And when you expand it out, it blows up quite a bit. So it's a pretty long set of rows. So I had to come up with some formatting to make it easier to follow. So yeah, so that's what I wanted to get some feedback on. But for today, let me put up the agenda. So as you know, we will be going back to volume 1. And if you remember, we had left off in one of the earlier sections on lists. And so there were 2 sections that we did not cover in lists. So there's doubly linked lists, and then there is something else following doubly linked lists. I forget what it is exactly. But the content, especially in doubly linked lists, relies on not the content, but the programs, the code, and the algorithms to some extent. They both rely on some MMIX features that are a little advanced. So I'm yet undecided whether we should have like a completely separate session on just those features, or we can manage to fit it into a a meetup that includes, an overview of the MMIX features and then do the linked list as well. Hopefully we'll be able to do the latter, so we won't need like a separate session. But yeah, so there are a few of those features, and but these earlier tree sections don't really need those things. So I felt this is probably a nicer start. It's also a nice way to go back to volume 1, that it's like a new topic, so you don't feel like this needs some other thing to be reviewed. But yeah, so that's the stuff for today. And I did see a couple of new names on the RSVP list, but again, I don't know if they'll actually appear. So let's go ahead and start. Yeah, but before we do that, let me show you the table. Okay, so if you happen to have that table 3 in front of you, page 165 of volume 3, remember? So these are the indices of the array, and then these are the keys. And this is the initial values of the links. So this much is pretty straightforward. So then what happens is that there are these passes, and each pass corresponds to sort of one complete merge of two lists that are sublists of this list. And the two sublists, the first sublist starts at index 0, so it's pointing to 1. And the second sublist, or the second list, starts at the other end of the array, and that's pointing to 2. And so you end up with this first list, it's got -3, which means that it's pointing to 3, but it's the end of a run. And then 3 points to 5, and then 5 points to 7, and so on, right? So you've got these two lists. So what's happening here is that at any given point, you have two source lists. And so I've called that out over here. So there's a source list, and these are the pointers or the links within that source list. And it's important to know that something is negative versus positive to know where there's the end of a run or the beginning of the next run. And then similarly, there's the second list. So there's always these two source lists. Then there is the output list, which is again, within this list, certain nodes are where we're going to start to append anything that's being merged. And there are two output lists as well. One of them is active. So one of them is actually going to receive the merged runs. The other one is inactive, and we keep switching between both of these. So the active list at the beginning is the first list, the one that starts at 0. And so then I've got this bar over here showing where is the current point where the merged runs will go to. And similarly, the inactive list also has a current point where when it becomes active, it will start to get the merged runs. And then these are the variables that are in the algorithm and their values. So with every comparison and then with every merge phase that happens, these things get updated. And so, for example, the source list 1, the first two keys that are compared are the ones that correspond to index 1 and index 2. So that's 503 and 87. And since 87 is smaller, that gets into the output list. And if you see down here, that's the active output list that gets the 2 link, as its sort of first record, and then the bar moves past that, and the inactive list doesn't change at all. And so then this goes on and on. So this is like, you can start scrolling through this, and you can see that. So it's a pretty long set of rows. There's many changes that are happening, and at any given point in time, you'll be able to see, okay, what are the 2 source lists that we're merging? Which one of the 2 output lists is active? And what is the merged result so far? If you go to the end, then you end up with just one merged output list that has all of the entries. So that was the expanded table, and I'll post this to the GitHub repo, and you'll be able to see it. But just to give you an idea.
Sounds good. I plan to debug the table later today.
Yeah, so that was another objective, was that if somebody writes their own code, they'll be able to match it up with this expanded table and see if your program is behaving as expected, or as at least specified in the algorithm. So yeah, so going back to our reading today, we are on we are in section 2.3. And that's pages 308 to 311. We'll spend about 5 minutes on this till 2:23. All right, shall we go over the section?
All righty.
Does anything need clarification here? It's just mostly definitions and terminology. Anything to comment on?
One thing I thought is noteworthy, although it was pretty clear, but it might have sneaked by with all of the diagrams, is that all of the diagrams show nodes with edges between them. And the definition, the formal definition on page 308, doesn't say anything about putting edges between these nodes. Right? A tree is a finite set of one or more nodes with this particular sort of relationship among sets of these nodes. But he never says taking two nodes and putting a line between them. Right? The lines are not part of his formal definition, which is fine. It's just if you only look at the pictures, you miss that.
That's a good point, that his definition then applies to a forest as well as trees.
Well, no, because his definition says there has to be one root. But he does say later on that if you have a forest, you can make it a tree just by adding one node.
Yeah, I guess a forest technically doesn't have a root, so yeah.
Right, but if you add one single node and call it the root, then you have a tree.
Yeah, you can.
And in particular, you don't have to add that node and somehow connect it to the roots of all the other, trees. Like, there's no connections, right? Just add the node, you're done. That's now a tree. There is no sense in this formal definition of the root node knowing anything about the structure of the other subtrees, knowing where their roots are. That there's no algorithmic component yet. This is purely math.
Yeah.
Well, technically, the fact that this set of subtrees have this root, that's the edge, right? That's literally, that's technically the edge. You are connected to your parent, and then you start like nesting them, and each subsection that's the edge.
Yeah, so I guess, Miguel, I think what Miguel is pointing out is that the edges are drawn in the figures, but they are implied in the definition. So he doesn't use the word edge in the definition, but the very fact that there is an association between a root and the subtrees, that is defined, and that, pictorially, that's an edge.
Yes. I mean, I wouldn't say there's a relationship between the root and the subtrees, but the root is the one thing in the tree that is not a part of another subtree. Right?
No, I would say, to me at least,
that's a tree.
Point B.
Every node in the tree is a member of one of its subtrees, except the root.
Yeah, but the subtrees are subtrees of the root.
No, they're not.
Yes. In part clause B. Clause B.
You say they're called the subtrees of the root. Okay.
Yeah. So I think that's sort of the edge definition. So he's not using the word or the term edge, but yeah, it's there.
Yeah.
But yeah, it's interesting to sort of analyze his way of presenting a tree. He's not using the word edge, but he's implying it. Yeah. Anything else?
I assume we stop before we get to the distinction between a tree and the binary tree.
Yeah, so this is still the end of page 3. Did I say 311? Yeah. So now we'll just continue with binary.
I have a quick frivolous comment.
Sure.
A few weeks ago, I was noticing that very thing, that computer science, the trees grow downwards. It's funny that probably everybody has made the same remark. They're like, what a minute, what are we calling these things trees? Actually, when I was explaining some algorithm that I was working on to my wife, I didn't call them trees or graph, I called them organigrams. That's exactly, because the trees in computer science look closer to how we represent a company structure than anything else that I know the software expert can relate to. Right? If you're going to talk to somebody who's never done computer science, you tell a tree, not a tree. It doesn't look at all like a tree. Mm-hmm. It looks like a compound organigram. And they get the intuition right away. That's it.
An org chart. Yeah. Although they do also somewhat resemble family trees. Although it's never really clear what we mean by family tree. It shows. He has two examples of things you might call a family tree, and they're completely different.
Yeah. Michael, are you having connection problems? You're muted.
You think?
Well, I mean, I don't know.
Google does not like me, and for my work, I'm on meetings all day long. It's like I don't have a problem.
Do you use Google Meet at work, or is it some other system?
No. Recently they switched to team meetings. I use WebEx all the time.
Oh.
Use other things too.
Okay.
It seems to be good now. All of a sudden.
All right.
It kept telling me it couldn't find my my camera, couldn't find my mic, then it couldn't find my network.
Well, as long as you're here for the discussion, it's okay to be disconnected while you're reading, I guess. All right, so we're moving to the pages right after 312 through 316. Another 5 minutes.
Am I still here? Yeah, I guess I am. Can you hear me?
Yep.
Do we need another minute or two?
Yeah.
Okay. Okay, so a couple of interesting concepts here. But let's first discuss Arthur's comments on oriented versus non-oriented or ordered trees.
Okay. I still have not really figured out what Knuth means here, but I do have some background that suggests to me that at least what I put there is probably what he's getting at, although I still don't see how that's any different from figure 19. And the comment sort of implies that figure 20A is in some way adding information to figure 19. That's how I read it. But in our definition of tree here, we have identified where the root is, and then for each of the subtrees, I've identified where the root is. There is another mathematical way to think about trees, which is just a connected graph where there's no cycles, right? And so you might have, what have I got that I could write on here? You might have a tree that looks, like that. That would be a tree, but it's not oriented in the sense that it's not clear, like, where's the root? Is the root here and it has 3 subtrees? Is the root here and it has 3 subtrees? Or, but figure 9, I mean, every tree that Knuth is talking about is oriented in that sense. They all have a root. So I'm not sure if that's what he meant or not.
He said something about sorting the subtrees. I was waiting for the punchline where you will know how to sort a subtree, but I didn't get that. So,
well, the subtrees might have an ordering to them. Like, he's not saying that there's a way to put them in the natural order, but he's saying
that's what I understood. Maybe that's what yeah.
No, the tree might come with index numbers for its subtrees. Right, like this particular subtree is number 1, this one's number 2, this one's number 3.
Right.
That's not something you can get from the structure of the tree. It's something that the person who made the tree has to tell you.
Right.
But then you can say, oh, these 2 trees are the same, except that this one has the 2 subtrees in the other order.
Mm-hmm.
So that makes
That's what I understood by that.
Okay, how about lists? Could somebody explain what lists are and how they differ from trees?
When you say list, you mean the weird list thing at the very end?
Yeah, exactly. The weird list thing, yeah.
Like heterogeneous list in. So it was funny because that looks like, so in Scala, you can generalize, in other languages, you can generalize like a class to an edge list, right? That looks remarkably like this thing. So you have like a regular class, you have a bunch of argument. I never remember the right word. Like the parameters of the class.
You mean the members?
Each parameter can
members of a class? Members?
Members of the sure. The members of the class, and each member, if member can be by itself, another class, and so on, so on. You can have like a tree. So in Scala, you can take any random class, not class. You have to be a special kind of class that everybody uses anyway, and you can make it an heterogeneous list, right? And each member also becomes heterogeneous. So you end up with a list of lists. It's tight, so it's a compile time. Therefore, you end up with a very long list, which each element of the list can be an atom, as he says, or another list, which in turn have you can also make a labeled heterogeneous list where each element you preserve the name, the string of the name of the member, right? So it's exactly what he's saying. And actually, I'm working on a project, and there are many others like that, where in order to compare two random classes in Scala, you transform them into a tree using this technique. And then, now you are not talking about classes, you're talking about regular trees. So it's, anyway, I have seen it in practice. What I'm trying to say, that thing that he's talking about, I actually use it in my code base in my company. We transform regular classes into these sort of lists and manipulate them to, you can forget about where it came from. It's just a regular list. Everything happens at compile times. It's kind of weird and mind bending, but it's there.
Interesting. Any other comments? I thought if we could just look at some of the exercises to clarify some of these concepts.
I did think that right around figure 7, his graphical skills broke down. Figure 7 is really the best way you could think of to indicate a structure with where it's like a tree, but some of the trees have the same element. It felt like surely you realize there's a better way to do this. It's just a graph with a cycle in it, or an undirected cycle. Treated as an undirected graph, it would have a cycle in it because M would be a child of both A and B. But he didn't draw it that way. Technical difficulties, I imagine.
Okay, any exercises that stand out for any of you?
He didn't mention a few exercises through the text, right? Like,
that's a good point. Yeah, I think that there was a couple of exercises early on for the binary tree. I seem to remember there was some alternative definition of a binary tree.
There is. there are non-recursive ways to define trees. For example, 10, 12, and 14. I don't know if that we need to look at those. That doesn't seem super important.
Exercises 1 and 2 should give us the answer to what he means by orientedness. So I'm
really?
Answers right now. I'm having a hard time finding them. Is this section 2? Yes, just 2-3.
Yeah, just 2-3.
How many different trees are in nodes A, B, and C? So that's the first tree, right? That's it, yeah. So there are how many different trees?
Huh, so that is interesting. It is what Sartaj said, that he actually says there are fewer oriented trees than there are trees total. So he's
right, because since ordering is not important, that means that a lot of them would get merged into the same class.
Yeah. Oh, yeah, so if the relative order of the subtrees is important, we say it's an ordered tree, but he also just sometimes calls that a tree.
Mm-hmm.
And if we treat trees as the same when the only difference is the order of their subtrees, then we call them oriented for some reason. Yeah, so that's the bottom of page 308.
I didn't look at that page 396, but is that part of that whole section on just oriented trees? I seem to remember that there is an entire section on oriented trees.
It's in the section on enumeration of trees.
Okay.
It's exercise 5 there.
Okay.
Oh, there it is. Wow, M25.
So in these exercises, meanwhile, 6 has a little triangle next to it.
Mm-hmm.
Define the statement. Define the statement.
Mth cousin n times removed. Okay.
This requires more knowledge of English than of computer science here, but here.
Right. So, Arthur, if you're familiar with the English usage, could you tell us?
So your nth cousin is the one where, if you look at your family tree coming down from ancestors, that you have your nth cousin is one where if you go up m levels and then down m levels, you get to them. So my first cousin, up m plus 1 levels and down m plus 1 levels. Right, if I go up 1 and down 1, that's my sibling. If I go up 2 and down 2, that's my first cousin. If I go up 3 and down 3, that's my second cousin, and so on. So
all right, so the way I understand it, first cousin is a child of a sibling of your parents. Right? I think it's exactly what you said. Sibling of your parents means that you go up 1 level and then you go sideways and then you go down 1 level. So that is a first cousin.
Yes.
So what is a second cousin? You go up 2 levels?
3 levels and down 3 levels.
You go up
or up 2 or go up 2 levels and over 1 and down 2 levels. But over isn't really an operation we have, so up 3 and down 3.
Okay, so that's second cousin. So what is first cousin? Is first cousin by definition 1 times removed or 0 times removed?
So the times removed is how many levels off of equality you are. So if they're 1 level below you,
once removed is the child or the parent of your cousin, which may have another name.
Right. And there may be a distinction between being like a third cousin once removed or a fourth cousin once removed. Like maybe the removing is only ever going down. I don't know. But yeah, it is something to do with being up or down one level from exact parity.
It's the number of levels difference, because if John is my third cousin once removed, then I'm also his third cousin once removed. It's commutative.
But you're also his second cousin once removed, right? If I have to go up 4 levels and down 3 to get to him, then he only has to go up 3 levels and down 4 to get to me. So
I see what you're saying. Yeah, maybe. I don't know.
Yeah, that's pretty much where I am too.
Okay. Yeah, I still don't get the removed operation exactly, but yeah, it's interesting.
Remove just means they're on different levels. Cousins are on the same level of the tree, right? They're
removed. So, but the different level is up or down.
Yeah, that's what we were saying. I'm not sure now.
Yeah.
Okay.
I thought.
So these are once removed.
I thought it was defined. I'd have to look it up. It is defined somewhere. I know that. But I don't know what the definition is.
Yeah.
Well, this is very relevant in the age of 23andMe. Okay. Yeah, I'm sure that if we can, this could be a valid interview question if you're applying for a programming job at 23andMe. How would you implement, third cousin 5 times removed?
Wow.
5 times. How about number 15? Invent a notation for the nodes of a binary tree analogous to the Dewey decimal notation for nodes of trees. This is again, referring to something in real life. But is anyone familiar with the Dewey notation? I've used it a lot in the past, but I don't remember the exact definition for it. I do remember that there's 3 digits that are separated by a decimal point.
That's right. That's right. It's not. I don't think it's really a very good example. Like because they go in ranges. They go in ranges. I think like the 500 number is science. So anything that begins with a 500 would be a book on science, and then. It's been a while, but
exactly. That's exactly right. Yes, you're right. So 500, let's say that's science, but then within 500, there's subcategories, right? So 530s will be something, 540s will be something. Go ahead, Arthur.
Right, exactly. If I remember correctly, 510 is mathematics, but 500 is general science. So it's kind of like
about page 313. He's not talking about Dewey Decimal. He's talking about page 313, where I do think misusing the term Dewey Decimal notation to just talk about what happens when you take the path down a tree and separate them by dots, right? The decimals here being just the decimal points.
Exactly. I don't think the Dewey Decimal System allows for 2 points. So if it's a tree, it's a very flat tree with
So the number of points in the Dewey Decimal notation representation of a tree or a representation of a node in a tree here is the path from the root down to the node itself with as many points in it as there are edges in that path. And if you do the same thing with a binary tree, you just label the left and right child, 0 and 1. Right? And then when you follow that path down through a binary tree, you're accumulating only 0s and 1s, and you end up with a bit string, a string of bits.
Okay, so I guess that's the key point, that there is a more compact representation for binary trees.
Yeah, I mean, it's only more compact in that the digits are smaller, right? There's only 2 possibilities for each digit.
Well, you don't need the...
It would be 3 possibilities for each digit and so on.
But do you? I'm wondering the decimal point, right? We can do away with the decimal point when we're dealing with binary trees, but then if we were not, then I think you would need the decimal point.
Yeah, I mean, if you were like serializing this over, a stream of bytes, yeah, I mean, you could replace the point, of course, with a slash or a space or whatever. And if you were doing it really at a computer protocol, you probably wouldn't use a separator, right? You'd probably use something like UTF-8, where you just say, just assume that this byte is an index unless the leading bit is 1, and then assume that the next 2 bytes and so on, right? You could come up with something that didn't use separators at all.
Okay. Let us read a little bit. There's an introduction to traversing binary trees. And yeah, so let's go ahead and read that, and then we'll take a break and come back and discuss it. Okay, let's take a break till 3:16, and we'll come back to discuss what we just read. So we're only reading till algorithm T on page 320. We'll save that for afterwards. See you. All right. Whenever you guys are back, let's discuss what we just read.
Alrighty.
All right, so the three kinds of traversals: preorder, inorder, postorder. Anything you hadn't seen before, not familiar with?
Not in my case.
Okay.
This is pretty standard CS stuff.
Mm-hmm. Anything to call out?
It talks at the bottom of page 319 about symmetric order, which is a synonym for in order, but I'm not sure exactly what use cases he's thinking of that make that name make sense.
Hmm. Yeah, an application in which there's symmetry between the meanings of the left and the right subtrees.
I would guess it comes when the trees don't have, when the tree isn't necessarily ordered. So, like for instance, I don't know, if there's no order between the left and the right subtree, then it doesn't matter which node you would process first. Maybe you could process them in parallel.
Yeah,
I guess in order has the property that, let's say what you're doing with it as you traverse it is like printing out the value of the node. Then in symmetric order.
Well, if you're printing it out, you're giving an order to them. You got to print out one of the nodes first. But let's say you were sorting the nodes. Doesn't matter which one you do first. Or let's say you were, well, yeah, let's say you were searching where the item that you searched for could only exist in one or the other. Doesn't matter which one you do first then. They're symmetric. You see what I'm saying? Oh, did I cut off?
No, yeah, no, we hear you.
Yeah, it makes perfect sense to me.
Okay.
Yeah, I was trying to see if I could come up with some more real life example, you know, not strictly algorithmic. But yeah, I'm not sure right now.
Sorting and searching, right? Didn't I give that? I mean, if you want to sort the sub list on, if the trees, well, sorting is kind of giving the idea of that there's an order. But if I don't know, if the items that if the job was to sort just what was in that tree and not to merge them, or even if it was to later merge them, but you start off by sorting the left node and sorting the right node, but it doesn't matter which one you do first.
Yeah, I think I see what you're saying, except that it doesn't feel that real life to me. It feels like that's sort of an implementation or algorithmic approach that you could take to the problem of sorting, which in itself is sort of a algorithmic problem.
Yeah, I'm thinking in terms of parallel algorithms, though. Like yeah, the sometimes the things that you want to sort are not supposed to be eventually merged, and sometimes you're looking for something in a list and you don't care whether you find it in the first subtree or the second subtree. You just want to find the first one. then it's symmetric. You just want to find anyone is what I should say first. When I say first, then I'm implying that one of them comes before the other.
Yeah, but Michael, the problem that I have with your example is that the traversal is not clicking with me. Like traversal to me or visiting implies that you're going to do things in a certain order where the order makes a difference in terms of like there's some processing that needs to be done.
I would say the order makes a difference except when it doesn't. There are cases where, like for instance, when you're looking for something and there may not be any kind of natural order, you just want to find one.
Yeah.
It makes sense to me. I've run into that situation.
Like a real life example, application? Like what domain was it? What was the actual domain, problem domain?
Well, I'm having trouble being specific about that.
Okay, well, when it comes to mind, let us know. Let's go on to the actual algorithm. So this is algorithm T, pages 320, 321. There's also a figure 23, which is the flow chart for the algorithm. So about 7 minutes on this. Okay, let's go over the algorithm. Could somebody summarize the algorithm?
Well, it's pretty much just a recursive traversal, except that it's not recursive. He's using an explicit stack, which he calls A, and we're seeing again this notation for pushing and popping on a stack with the double arrow. And he's using the stack to basically the first thing you do is go down the left edge of the tree pushing onto the stack. And then finally you do some stuff and you use tail recursion in step T5 to sort of visit the right. Anytime you need to go right, you do tail recursion. Anytime you need to go left, you push on the stack. And then when you get finally to a leaf, then you start popping from the stack to get back to places you still need to visit their right child of.
Which is essentially recursion, right?
Yes, except he's not doing a recursive call.
No, I know. He's not using recursion in the language, but technically, if you push stuff to the stack and pop things from the stack, it's almost recursion. I mean, that's how many things are defined in recursion. I mean, yeah, you're right. I'm not saying that you are right. I completely agree with you. Just saying that
call instruction on most architectures is just a push onto a stack, a designated stack, followed by a jump. So anytime you are pushing onto a stack and doing a jump, you can think of that as a call.
Yeah, a difference between this is, I would not describe this as recursive at all. A difference is a recursive program will put the return address of the next instruction to execute onto some kind of stack, except maybe for the case of tail recursion. But this doesn't put any address of the next instruction to execute on the stack. It puts only data on the stack. And it operates in a kind of a really a loop. I guess you could look at it as a loop that starts at T2 and keeps on going. It's like a while P is not known. Or P is not whatever that character is. You could start writing your loop that way. But it's going to be a while loop rather than a piece of function, a piece of code that calls itself. So it's not recursive by that definition.
No, I agree 100%.
It is a recursive algorithm.
Okay, so
exactly. So
any point of confusion about the algorithm, or
can't wait to talk about the proof.
Yeah. So Miguel, you want to take a stab at summarizing the proof?
I can't wait to. I can't wait to somebody else talk about the proof so I can understand what it was going on there.
So I do realize that we did not actually cover induction. That is, I think there's at least one section, maybe a bit more, in the mathematical preliminaries portion of TAOCP. So we could do that at some point. But if you've used induction before and care to explain this, or you could even just give an explanation of induction together with this.
I mean, I will give whatever I remember, which is induction. You have a base case that is known to be true, and then you assume that let's call it the n-1 case is true. Then you just prove the current one, and that means that so the base case is true. And everything up to the previous case in the previous case of n, whatever n is also true. Then you just prove that the new step makes the thing to still be true, right? So
what is
the part that
what is the statement here? So applying your explanation of induction here. So for example, what is the base case here?
The empty tree, right? Yeah, and it was equals 0. Then
not an empty tree, not an empty tree, an empty stack at step.
Empty stack.
An empty stack. The way to understand
is it an empty stack, Michael? I think it's an empty tree.
An empty tree.
Page 321. This statement is obviously true when n equals 0 because of step T2. That's your base case.
Well, okay, I think. Okay,
I think the confusion or the problem is that we've got two variables here. There's the size of the tree or the length, whatever you want to call it, the number of nodes in a tree, and then there's the size of the stack, which is m. But here the induction is on n, the size of the tree.
Well, no, I don't think so, because well, here's why. Okay, I think of it as A1 through AM are pointing to parents of the node that you're working on. So it's not an empty tree, and the base case. I mean, it's an empty tree. The base case is that you're at the bottom level, so in that sense, there's an empty tree, but the stack doesn't have to be empty.
The lemma we're trying to prove here is the one in italics on page 321, starting at step T2, with P being a pointer to a binary tree of n nodes, and in the base case, n is 0. Right?
Okay, you're right. Okay, I see it.
Are themselves binary trees.
I see it.
And that's important because, Michael, as you were saying, the induction is on the size of the tree. And so when you're looking at, the left subtree and the right subtree, then you can apply the inductive hypotheses on those.
Right. T2 is working at a node in a tree. It's not. It doesn't say that it's the entire tree.
Mm-hmm.
That's the way I was looking at it. But in the 0 case is where P is pointing to a subtree of that has height of 0. That is a one level tree, and then it's saying if that's the bottom level of the tree, then the lemma is obviously true. And we don't care about. Throughout all of this, we don't care about what's on the stack A1 through AM. They point to nodes above the node that P is pointing to, and the algorithm and the well, that's the way I'm looking at it. Maybe I'm wrong. Doesn't matter what those are because we never open those up.
Maybe instead of trying to understand the proof, maybe we should just first try to explain the statement.
The big statement. The problem with this algorithm, or the problem, is that I get it. I mean, I can sort of visualize the whole thing going, right? Like you keep you go to the left, and then every time you find the root, you just the sub root, just put it in the stack, right? And when you've reached the end, you say, okay, so now I go to the stack and just go back up.
I think what it says is that when we arrive at T2 with a stack that's somewhere in the middle of traversing a big old tree, when we arrive at T2, we're going to traverse everything below T2 in order, and the stack is going to be the same when we come out at T4.
So why would that prove that the traversal was in order?
Oh, it's not. That doesn't prove it. What we're trying to say is that when we follow this algorithm to traverse the subtree in order, it has a stack when it comes into T2, when we finally reach our node. And what this lemma, all this is saying is that by the time we finish traversing in order, we will arrive at T4 and the stack will be the same. That's what we're trying to prove.
What do you mean the same? The same as what?
the same as what it's, so when we come into T2, there's a stack, and it has A1 through AM. And when we come into T2, we're going to go and visit the left, then visit T2, then visit the right. And while we're doing that, we're manipulating the stack. When we finally finish, we're going to arrive at T4, and the stack will be the same. That's what we're going to arrive at T4 many times if it's a middle level tree. But when we get to when we finish traversing the subtree in order, we'll be at T4, and the stack will be the same. That's what this is trying to say. Never said that A1 through AM are parts of our tree. As a matter of fact, it really says that they're not, because it says that when we get to T4, we finished traversing in order, but we still have all this stuff on the stack, the same stuff that we started with. Yeah, I think that has to be right.
Well, there's a proof, so maybe you can just step us through the proof.
Well, the proof is, okay, it's proof by induction. So when n equals 0, we what does T2 say? What does T2 say we do? We're going to go right to step. We're going to visit. The only thing we can do is visit what's at T2, and there's no nodes to follow, so we go immediately to T4. We never put anything on the stack. That's the base case. So the base case says that if the level of the stack at T2 is 0, then we arrive with the same stack.
Not only do we arrive with the same stack, but we have traversed the binary tree in question in order.
Right.
Right? And it's an empty binary tree. So yeah, we're done trivially.
Right.
Okay.
And now to prove it, you're going to assume that it's true you're going to assume that it's true for trees of height n-1 and look at what happens with trees of height n. If you came to step T2 and your subtree is of height n, then what's going to happen? You're going to first visit.
Michael, would you mind following the terminology in the proof where he says let P0 be the value of P when we enter step T2?
Well, let P0, okay, P0, okay, we're gonna, yeah, okay, so when we visit the left subtree, the first thing that happens before we visit the left subtree is we put P0 onto the stack. So what we're doing on the left subtree, we come in with a stack that is A1 through AM plus a P0. But that's not really important. What's important is that the left subtree has height n-1. So we know that the algorithm is going to do all of the left subtree in order. And when it exits out, the stack is going to be the same. It's going to be with that P0.
Isn't it essentially that we first put in the stack all the left, and then we put in the stack all the right, and then you just start popping stuff from it? Sort of? No, not true.
Not true.
That's not right.
That's not really right.
No, that's not true. No, I realized it. Sorry. I had to say that out loud to realize that it was just possible.
Okay. And then what are we going to do on step T4? What is it we do on step T4? The stack is empty, the algorithm terminates, but it's not. So we take that P0 off the stack. And we we have to end up going back to the,
then we go to step T5. So after T4, when you've popped the stack, then you go to T5.
And we're going to do the right subtree. And it's the same thing. The right subtree is also of height n-1 because the parent is of height n. And so the same thing happens. Only
Okay.
P0 at this point is going to be the top of the right subtree.
All right, I think I certainly understand it a little better.
Yeah, and all this time we never, what was on the stack when we came into the subtree at the initial P. Is that what it's called?
P0?
The initial one. No, the initial one. I've lost my place. It's P is a pointer. The initial P. Yeah. P is the subtree. Starting at step T2 with a P, a pointer to a binary tree of n nodes. P0 was once the binary tree of n-1 nodes that was the left child of P, and then again it was the right child of P. As we went through the algorithm. Right?
Yeah. Okay, so then there was some notation. Any comments on the notation? Is that pretty clear? He's given some examples of applying it to that tree.
No one would do it that way.
I'm sorry?
I'm still getting used to
No one would do this way. I mean, why wouldn't you say P dot preorder successor?
Well, it's short and sweet, so that would be my guess. I haven't seen how he's going to use this, so don't really know. But Michael Lane, you had a comment?
So I'm very new to the notation of trees, so I'm still trying to understand like what the arrow means and stuff like that.
Yeah, we can actually just quickly tell you what that means. So the arrow, the left arrow, right, with the arrowhead on the left, that's assignment.
Okay, so that's so it's like assignment in R. Okay. Okay.
So
well, except that he's assigning a pointer to a stack, which is, or like in T3 he says stack from the pointer.
Well, the double arrow is different from the single arrow. Remember,
yeah, that's what I mean. I'm not getting what the double arrow means.
Yes, the double arrow he's using to mean push and pop on a data structure.
Oh, you're right. I see.
It's a stack.
Okay.
He's saying take P and put it into the stack, and then later in step T4, take. Yes, well, this is actually even weirder in that I guess the title of the step is also part of the step. This might be the first time he's done that. I hadn't even noticed that.
The title of the step is part of the step?
Yeah, the thing in the brackets. You have
the thing in the brackets.
Oh, no, I'm sorry.
The brackets is something that you're supposed to do.
No, okay, yeah, I missed the next line. This is fine. So the thing in the brackets is the title of the step. And he's saying, if stack A is empty, terminate, otherwise, and then he says P double arrow A, which means pop something off of stack A and put it into
pointer P from the stack A. So,
right.
So yep. The way I read those arrows is from. So the single arrow in step T2, P from the L link of P, or assign P from the L link of P. And the double arrow is the same thing. It still reads as from, but the thing that you're getting from is an element, and the thing that you're getting it from is a whole stack. So it means that the stack is going to have one less level, and P is going to be assigned from whatever was on the top.
Thanks, Arthur and Michael. Does that help, Michael Lane?
Yeah, it helps a little bit.
Okay. Yeah. So the notation, there's the double arrow, there's the single arrow, And then there is this sort of a function-like notation where there's like a name and then parentheses, and there's some sort of something in the parentheses. So that notation where it, for example, says L link of P or R link of P, you can think, or at least I think of it as a field notation, where in programming languages you would have a dot. So this would be the equivalent of, let's say that you've got some object P. In this case, it happens to be something that's being pointed to, but then L link is a field in that object, and then R link is another field in that object, or like a data member. So this is sort of retrieving the value of that field.
Oh, so you're linking the attributes of the object. Okay, I think so.
Yeah. So P would have an L link and an R link, and presumably it would also,
which you're right.
It would also have data.
Yeah, except it's used, this notation can mean different things. So for example, node of P is the actual object, like the whole object itself. And then there's like, you'll see info of P is something else that he will, like explain what it is. So he uses this in many different ways, but you'll get used to it. There's not a lot of it. But yeah, okay, cool. Let's see. What about, yeah, I don't think there's anything else here. So P star, P dollar, P sharp, and then star P, dollar P, and sharp P. We'll see how these, sharp P, yeah. We'll see how these play out later. But let's go on to the next couple of pages, which introduce this concept of threaded trees. And then there's a variant of the algorithm we just saw for threaded trees, which is an optimization of a kind. So about 5 minutes on this, till 3:58, 3:59.
Okay, I got it. Those pages.
Okay, sorry about the page numbering. That is something Arthur correctly points out. And yeah, so who can explain threaded trees? I guess if we can just maybe explain that that little table, although it isn't labeled as such, the bottom of page 322, where you've got the unthreaded representation and then you've got the threaded representation of the equivalent thing.
Yeah. So what we're doing here is anytime we would have a null pointer in the tree, which he's using capital lambda to represent null, remember? Anytime we would have a null pointer as one of our children, we can use that space for another purpose. And we observe that a very common operation here is in-order traversal. And in-order traversal is actually really easy because the next node you're going to after this one is always a member of your right subtree, unless you haven't got a right subtree. If you haven't got a right subtree, then your right child pointer is null, and you need more information about where to go next in your in-order traversal. And so we just combine those two observations together and say, well, let's use this space that we would normally use for our right child. Let's use this to hold a thread that connects us to our successor in the in-order traversal order. And so we do that every time we would have a null child on the right. And just in case we want to traverse in order, but right to left, like backwards traversal, anytime we would have a null left child, we're instead going to have a thread linking us to our predecessor. And then node D and node J on figure 7. D is the first node, and J is the last node, the rightmost node. So for them, they haven't got a predecessor or a successor, respectively. And so those threads are currently just kind of dangling. But he says we'll see what to do with those later.
Yeah,
That's great. Any questions about this and how the representation lets you know that there is, like, what is the meaning of the link? How is that being done?
I think Michael was going to say something else. What were you going to say?
Go ahead, Michael.
I was thinking it feels like he's introducing like a chirality, or what metaphorically is a chirality to these trees of in order being left and right and stuff. But that's the sense I was getting as I was reading this, but I wasn't sure if I was right.
I don't know the meaning of chirality. Could you tell me?
So if you look at your hands,
Handedness.
and if you flip your hands back, it's like either left-handed or right-handed in terms of the shape. And chirality usually has to do with like chemistry and stuff, and different chemical properties depending on the orientation change. And so he's basically introducing, what I'm saying is he's introducing like an orientation to the tree.
I would say yes. On page 319, when he defines these three kinds of interesting traversals, in every single one of them, he's doing the left subtree before the right subtree.
Right.
It is privileged in that way. And you could imagine three more kinds of traversals. Like there's a reverse in-order traversal where you do right, then yourself, then left. But there's also like reverse preorder and reverse postorder that do... Right. Like reverse postorder would be like traverse the right subtree, traverse the left subtree, traverse myself, or visit myself. So yeah, so that's not really introduced here. It's just sort of been carried through from earlier.
Okay, so it's been carried in.
Adding these threads is symmetrical, right? There's all whatever you're doing with that right hand thread, you're also doing the same thing with the left hand thread. just in the other direction.
True. Okay.
Right-hand threads always point to successors, and left-hand threads always point to predecessors.
Yeah, and that's why I felt it was a dumb question. Because
no such thing, Michael. No such thing as a dumb question. So please, the dumber the better, actually. So we are a little past 4. Is everyone okay to keep going till we finish this section?
I'll have to drop off
I'm sorry?
but I'll have to drop off soonish, but I don't mind keeping going. I can always drop off if I need to.
Probably another 10, 12 minutes at the most. Okay, yeah, so let's go on to the actual algorithm. And, because the threaded representation does help a lot, the algorithm is pretty simple. So let's spend about 3 minutes on that.
The algorithm is shorter because it does less. It only finds the next successor. It does not traverse the whole tree.
But what do you mean it does not traverse the whole tree?
All it does is find the successor.
Yes, I put that comment just now in the chat. This is not a version of algorithm T designed for threaded trees. This is just the one little bit. And algorithm T itself would now be call this in a loop.
Yeah, that's a good point.
Call this in a loop with a stack. This doesn't need a stack.
The counterpart to this for use with non-threaded trees would be like algorithm S prime, which is sort of the first part of this, but then if the R length of P is null, then you're just out of luck. You can't find the successor. There's no way to find the successor. So that's why algorithm T needed that stack. Whereas an equivalent, algorithm T for threaded trees wouldn't need the stack.
Yeah. This is like, as he says, the following algorithm just calculates the successor given P. What about the comment at the bottom of page 323? In view of the loop in step S2, would it perhaps be faster to use a stack after all, as algorithm T does? Did anyone get past that first paragraph on page 324?
Well, I think that's a question that he's going to answer in the analysis, right?
Mm-hmm.
But if we're actually using it to traverse the entire tree, then that loop is also happening in algorithm T as well.
Yeah.
Right? This is doing strictly less work to traverse an entire tree than algorithm T was doing, because T had to do that loop on the way down and then a similar loop again on the way back up. Here we're cutting out that similar loop on the way back up. We just jump right back up to where we need to be.
Where in the did you guys see that? What paragraph? Because I didn't get to that part yet.
At the very bottom of page 323, he says, we claim that algorithm S is equal, although this property, etc.
Yeah, whoever gets through the first sort of 3/4 of page 324 till just before the program is introduced, please feel free to go ahead and explain that.
The two tag bits.
Michael, did you have a comment?
No, I was just reading.
Okay. Okay, so anyone figured out that diagram on page 324, how that's being constructed?
The only thing I don't get about it is why on the list head does he have that right pointer point back to itself? Just to have something there?
I feel like that's null.
It's not null.
Yeah, it's not null. It's not null.
It's not null. Like if you look at D has both. Well, actually, it's a threaded tree, so okay, no. Yeah, I mean that's what I think it is too. I think it's null, but why wouldn't he have put a lambda in there then? But other than that, when we looked at the threaded tree in 2 pages back, from the very first element, the left link went off to nowhere, and from the very rightmost node, or from the very last node, the right link went off to nowhere. And he says it works better if you make these if we just add this new list head and make those links point to that list head, and now what you have is a circular list.
So I think this is what he was referring to back there, that we will see later what those special 2 threads are going to be used for. And in the set of equations labeled 8, he shows our link of head is head itself. So it is pointing back to the head node.
Well, I agree that's what he's doing.
Right.
The question is why? Why wouldn't our link of head be lambda? You need L link of head. You need L link of head to be A so that you can start the tree. I kind of get that. And
well, that way it's not completely circular. No, I mean,
if you look at that new list head as another node to a tree.
So the head is also the tail?
Well, that's what it's saying, but why?
Well, I feel like he was getting rid of all the his goal was to get rid of all the lambdas in terms of how he's creating these threaded trees.
Okay, but why?
Good question.
He got tired of seeing null pointer exceptions when he was debugging this? I don't know.
That's what I
wanted to see an infinite loop.
So, yeah, I think that's a great question. There are 2 more algorithms remaining in this section that we're going to cover in the next meetup.
We'll probably get an answer.
Yeah, I have a feeling that's where we'll find the answer. Yeah. Okay, so yeah, so I think that that will do it for today. We'll see. We could cover the programs next time, or just go on to the algorithms, the new algorithms directly. But in any case, we are still in this section, and so we will continue traversing binary trees. Those are the 2 algorithms, I and C, that I mentioned. We'll cover next time, and then there is the next section, binary representation. So the addition is, Michael, in response to Michael's question, we're just using I should say that my references are to the most recent editions of every volume. But, if you have an older edition, and I believe Michael is using at least one older edition of some of the volumes, and so if you can figure out like which pages correspond to what. But generally, I think the sections have not changed a lot. Is that right, Michael?
The only thing that was changed was actually the MMIX thing.
Okay.
This one, the page numbers seem to be the same.
Okay. So the page, maybe there's not a significant difference, but this is sort of I guess it's showing up reflected, or Yeah. So here, this is sort of the updated code for all of the editions, and for at least for the first 3 volumes. So we do use these, the code from the MMIX supplement in parallel with TAOCP. But other than that, yeah.
So I'm new to trees, actually. I'm glad I'm kind of learning this. I know this is a lot of the advanced stuff. I have a lot of different books, so this helps me actually understand the book that I got that's just called Algorithms and stuff. So
Is that the one by Sedgwick?
No, it's by like some Sal. It's the one that Georgia Tech uses.
Okay. Yeah, so Knuth does introduce everything from scratch. So he doesn't, the only thing that he has asked for, like way in the beginning when we covered the preliminary stuff, was that readers should have written like 3 or 4 programs. But in terms of the basic concepts and the data structures and the algorithms, he doesn't assume anything, or he doesn't use, like other more fundamental sources. He does develop everything from scratch. Now, having said that, we have covered a lot of the earlier sections in Volume 1 where he develops lists. And a lot of the notation is coming from those sections, and some of these things like the list head and his peculiar way of constructing lists for certain purposes, those are coming directly from previous sections. But there's not a lot of those sections, so you can go back to those sections and review them, and all of our previous meetings are recorded, so you have access to a lot of resources. And then, of course, you can always, whenever you join, you can always ask, what does this mean? And I don't know what this is. I haven't seen this before, and we'll explain.
Thanks, yeah. I didn't have opportunities so at Georgia Tech, when I graduated, the computer science program didn't allow other people to join. So I'm kind of new to a lot of this and catching up. It's a lot better now.
Okay.
But these are kind of cool. I didn't know this guy was still publishing, and I was like, oh, he's still doing stuff on lists? That's actually kind of cool. And trees. Because in the meetup that you said, right?
I'm sorry?
That this guy, the author, is still doing research in this, right?
He is, yeah. He is. He's
kind of cool.
Yeah, he's really active in terms of publishing, but he's even seems to be more active in terms of just presenting his material and giving talks and video interviews. And there's so much stuff on YouTube, just very recent, like within the last 2 or 3 years. So it is pretty amazing. And yeah, and a lot of his research is on trees. I mean, he's well known for many algorithms on trees and graphs and lists. And what's actually interesting in terms of my sort of development, going through these meetups and reading the text closely, is getting an insight into the way Knuth approaches problems. Because even though a lot of these algorithms are very standard and well known, his take on them is generally a little different, and at least his presentation is very special. And I feel like it is reflecting the way he approaches problems at a very sort of low level, and this very step-oriented manner. So yeah.
Cool. I mean, it's a lot easier than the one I was reading. It's just like, wait, why is this true? But he also feels like he's Griffiths. Griffiths have you ever read anything by David Griffiths?
No, not
Or
really.
you know who that? Okay, Griffiths is considered the modern way of teaching quantum mechanics, and probably teaching the prefaces to quantum computing. His book is considered the easiest of them all. But what David Griffiths does, which is evil, is he'll leave some of the most important like proofs and concepts as exercises for the student. And it feels like this guy's doing the exact same thing when I was reading this.
Yeah, well, you'll definitely, develop an opinion of Knuth. I mean, everybody does as they go through the text.
I mean, it's a good thing that he does, but it definitely feels like this is the book you would present at a university for your students to like go through, you know?
Yeah, one thing I would say in that regard is that he does provide answers to every single exercise. However, a lot of the answers are more like sketches or outlines. They're not like completely complete with all of the details, but they are enough to give you a pretty good hint about what to do.
That's good.
Yeah,
that's good.
So,
are there any university courses that use Knuth for the textbooks? I doubt it. From what I've seen, I doubt it highly.
I saw a paper by one person who has collaborated with him in the past, and he actually wrote a paper on teaching a course that used TAOCP. So I think you're right, Michael, that it is.
Right.
It is,
if I heard of a course that uses TAOCP as the textbook, I would think that the professor must be Knuth.
it's a one-to-one correspondence.
Now, what if he does? If he does, we need to find recordings of him, because the second most important question is, does he talk like he writes?
Apparently, there's a lot of lectures on YouTube that you can listen to. I haven't listened to any, but apparently there are.
Yeah, I think that they're a lot of fun. I've actually watched quite a few by now, and but just like the text, there's like a never-ending supply of these videos. So there's a lot of material. He's very expressive. You know, he doesn't shy away from explaining anything at all, like whether it's related to computer science or program. I mean, he just talks about a lot of different things, and so I think that he's a great speaker in that regard. Like he just is very, very articulate and expressive. So yeah, so hopefully you'll continue. By the way, where are you connecting from, Michael?
Georgia.
Oh, okay. I guess we should have guessed.
Normally I'm at work. I can sneak into work on Saturdays at the courthouse and bum off their Wi-Fi, bum off the judge's Wi-Fi. But I can't do that today because for reasons that should be obvious if you've been listening to the news and stuff. Everything's going to be shut down at least until Thursday.
Oh, wow. Okay. All right, cool.
Basically a precaution. And we're all working from home, basically.
Yep. Well, we hope that, you will have access to great Wi-Fi every Saturday, and you can join us. So it's good to know that you're in the same time zone, so it's not an inconvenience in that way. But yeah, I'm in New York, and most of the other people are also in the New York area. So, but from time to time, we've had people join in from other parts of the country and sometimes even other parts of the world. But these are the regulars that you saw today. So great. Very nice to meet you, Michael. Have a good weekend.
Yeah, I gotta actually, do you guys publish papers ever?
No, the intent right now is really to focus on the algorithms and code in TAOCP, because as you can see, there's just a lot of material and many different types of material. There's a lot of mathematical material. There's a lot of, algorithmic and coding material. There's a lot of conceptual material. So you sort of have to pick and choose, like in terms of time and what is sort of the biggest value that people can get. in a sort of community-based reading group. And I felt like if you,
I was asking more if you guys did that like professionally, what your guys' background was and stuff.
well, I don't really know. We generally don't have a lot of time to delve into that. So I don't know if people have published papers or not. But yeah, I mean, feel free to bring it up next time. I mean, certainly reading TAOCP, you'll see there's a lot of references to papers. In fact, one way to describe TAOCP is that it is really a distillation of many, many papers, right? Presented in sort of a more accessible and
which is why I
somewhat...
compared it to Griffiths, which is exactly why I compared it to Griffiths.
Okay,
because
cool.
Griffiths, if you read Griffiths, you basically have the history of quantum mechanics for the last 30 years.
Oh, wow.
Distilled into one book, with the exception being quantum computing, which it just does not get to. It gets to all the other aspects of quantum mechanics and atomic physics and the hardware of quantum computing, but it doesn't go there. It probably has a later volume if enough stuff comes out, but yeah.
Okay. Great. So these are some of the resources that we're building up, right? So we've got all the recordings, all the meetups recorded on the YouTube channel, and then the chat and some other notes about each meeting. Those are in the GitHub repos, as well as a lot of code by now, both the assembly MMIX code and quite a few C implementations of the algorithms. There's also a Facebook group. And
the art of computer programming. Gotcha. I got it. I see it. Nice.
Well,
nice.
Thanks again for attending, and hope to see you next time.
Yeah.
Bye-bye.
Right now I'm preparing to go back to college, and there's some prep work I need to do. So I'm hoping to take a prep course in data structures and be ready for the fall. So.
Well, hopefully we can help you in any way possible. So that's great. Bye.
See ya.